Hey, welcome back to Math with Patrick. It's January 7th. We got another problem from this calendar. Let's get on into it. Let's find the sum, so that means adding stuff up, of the roots of this polynomial. A root is a certain value of x such that when I plug it in to my equation, I get a 0. So that's what it means to be a root. And looks like we need to find a few of them, at least two, add them all up, and we should get 7 out of it, because the answer for these problems is always the date. So let's try it out, and I'm a little bit hesitant about this one. That's because we're being asked to solve a degree 8 polynomial, and these ones are really tricky for higher order polynomials. Quadratic equations have been extensively studied, and these ones are when your highest degree is 2. Cubics are a little bit harder, but it's not that difficult to find a solution to cubics. Though once you start getting to degree 4, 5, 6 polynomials, those get pretty tricky. So 8, I'm a little bit worried about. So the first thing I'd like to check is whether or not I have any rational roots. A rational number is one that can be expressed as a fraction, where we have like a whole number up top, a whole number on the bottom, and this one can't be 0. So I want to do this first just to double check whether or not I have any roots of this polynomial that are like not too complicated. And I'm going to use something called the rational root test or rational root theorem. This states that I can make a fraction out of one of the factors of this final constant divided by one of the factors of this leading coefficient. Now, there isn't actually a leading coefficient here, so we can just pretend that there's a times 1. And once I get this fraction, it could be either positive or it could be negative. So factors of 8 include, well, 8, 4, 2, and 1. And then factors of 1, well, that's just 1. So it looks like the potential roots, if they are rational, include 8, 4, 2, and 1, both positive and negative. So let's test out these candidates. As a reminder, a root, again, is a number that I can plug into the function such that I get a 0 out of it. So if I try plugging in 8 into my function, that obviously isn't 0. Okay. If I try plugging in 4, that's way too low. 2, 1, that got kind of close. So this kind of tells me that I have a root nearby 1. But since this isn't a 0, 1 is not a root. It was just kind of near it. Okay, let's try some negatives. -1 also doesn't really work. -2? No. -4? 8? Okay. Well, none of these gave me a 0 here. I mean, this one was kind of close, but none of these are actually roots. So I just wrote out a list here in Desmos. This one has all of the roots that we just tried. I also wrote a little function here that counts how many of the number n I have in my list. And so this right here just tracks that I'm trying to ask Desmos, how many zeros do you see in the list R up here? And Desmos is telling me 0. I don't see any zeros, so I don't see any roots. So we have no rational roots, and we need to find roots of this polynomial. Where are they? Where are they hiding? We could check the graph. That's one place to look. So if I zoom out and find the curve, there it is. These x-intercepts tell me where some roots are. That's because an x-intercept tells me a value of x such that my function's value is 0. And so using a bit of technology, I have found 2 roots. I know these are irrational because we just did that rational root test and none of them worked. So I have 2 irrational roots here. Now if I add them together or find their sum, that's about 1 plus about 7. And so that's going to be 8 if I round. And that's not 7. Today's January 7th, so I was expecting a 7. So what gives? There is another math concept called the fundamental theorem of algebra. This one states that the degree of any polynomial is equal to the number of complex roots that we have. And the key here is complex. A complex number is one that can be written with a real part and an imaginary part. And so far, we have found two roots, two real roots. They just happen to be irrational. And the fundamental theorem of algebra suggests that there are 6 more that we haven't found yet, that the Desmos graph wasn't powerful enough to find for us. And so here I'm asking my handy dandy Wolfram Alpha. This is my other online calculator that I like to use. And this one does understand complex numbers. And this one will help us find the other 6 missing roots. And there they are. So I have 1, 2, 3, 4, 5, 6 complex roots. And you can even see that they graph these roots for us. Here's that 1, here's that 7, and then these 6 complex roots, you can think of them on this complex plane where they aren't going to show up on that Desmos graph because that only shows us real numbers. Here we can see all 8 of our roots. Now having all 8 of our roots, we can just add them all up and hopefully we get 7. One thing I notice is that these imaginary parts, it looks like they come in pairs. So this negative 0.42 cancels out with the positive 0.42 when I add them up. Same thing with this pair, those imaginary parts are going to cancel, as are these ones. And then it looks like for this polynomial, these real parts are the same. And so when I add them up, I'll add this number, and then twice this root, plus twice that, plus twice of that. And I typed it all out up above. So here's the first real root, the second real root, and here are those pairs that I typed in. And hitting enter, adding these all up, we get exactly 7. And there is a 7 we were hoping for all along. That's today's date, January 7th, and we have found the answer to this very complicated problem. So here's all the work it took to solve this problem directly. Here's the polynomial we started with. Graphing showed us that there's 2 real roots, but the complex ones were harder to find. And it took an online calculator to figure out the other 6 roots, and then finally adding them up did actually get 7. Now, there is another way to go about solving this problem, and that's what this epilogue is going to be about today. It's going to be a bit lengthier than normal, but I wanted to show a different way to solve this problem. As I said before in the video, the fundamental theorem of algebra states that for a polynomial of degree n, I'm going to have n amount of complex roots. So for this particular example, knowing that the degree is 8, I'm going to have 8 complex roots out of this polynomial. And for this second way of solving it, I'll pretend that I don't know what they are just yet. However, I do know that if I wrote this degree 8 polynomial in factored form, I would have 8 factors, 1 for each of my roots. And it'll look like x minus the first root, x minus the second root, and so on and so forth. And the reason why this works is that if I plugged in that root, say r1, into this factor, then r1 minus r1 is 0. And it doesn't matter what all of these other factors are when I plug in the first root. They're going to multiply out to something, but then multiplying it by this first 0 will make my function's value 0. Now we need to think about relating that factored form back to the standard form from above. So that first term was x to the 8th, and this one comes from multiplying all of these x's together. When multiplying a long list of binomials, you can kind of think about it as walking past each one and picking up a certain term along the way. And to get this x to the power of 8th, as I'm walking along each factor, I have to choose x every single time to make sure that I get 8 x's all multiplied. So walking along each of these factors, I'm picking up an x each time I come across one, and that's where this x to the 8th comes from. To get a term with x to the power of 7 in it, I'll have to go over all of these different factors, and at some point, I have to choose not an x. And then I got to choose all of the other x's, and eventually I will have 7x's all multiplied times a negative of one of the roots. Now, it's kind of arbitrary that I chose R4 right here. I totally could have picked like R2 along the way and then taken these x's here and here. And that is true for any of these roots. So for my x to the 7th term, I could get that by selecting 7 of the x's and then multiplying it by one of these roots with a negative sign on it. So that could be negative R1 or negative R2 or negative R3, and you kind of get the gist. And so now I have a long list of all of my roots being subtracted from each other, and that's not exactly what I wanted because I wanted the sum of all the roots. Now it's not that much of an issue because I can factor out a negative from all of these different roots, and a -1 would pop out. So I guess I'll just say like a minus right here instead. And then I'm going to rewrite it a little bit. I'll have x to the 8th minus all of my roots added up, and then the x to the 7th over here. And this x to the 7th term here has to match the x to the 7th term from the original polynomial. So looking up here, it has to match minus 7x to the 7th. So all of this has to be minus 7x to the 7th. And everything just kind of lines up. This minus sign is right here. This x to the 7th is right here. So the sum of all of my roots has to be this 7 right here. So you don't even need to know what all of these roots are to find their sum. Kind of strange. But that 7, the answer to this problem, was hiding right here in the problem secretly. This was the answer to this question. And now we are really, really done. Proving it 2 different ways, getting the sum 2 different ways. Whew, long problem. Thank you for sticking it out with me this whole time, and I'll see you tomorrow. All right, bye.